Okay, so our last speaker for the afternoon session is Professor Jiehang Zhang from BIMSA. He's going to talk about quantum information experiments with atomic qubits in high dimensions. Let's welcome.
Okay, thanks for the introduction. So it's really a pleasure to be here to share with you some of our results. So we're using atomic qubits to do experiments, and I will share with you, talk to you about two types of atoms, charged and neutral atoms. So here's a brief outline. After the introduction, I will briefly mention the importance of dimensionality and qubit connectivity in quantum information systems. Then I'll tell you about trapped ions in high dimensional spaces, and then a 3D trapping of neutral atoms with a little bit of outlook at the end. So I always like to introduce with this slide. So we say that a quantum computer can potentially have exponential power. This is, in fact, arising from two relatively simple rules of quantum mechanics. Rule number one says that the Hilbert space scales exponentially with, for example, the number of constituents, such as spins. This is essentially a wave interference effect because we have to describe the probabilities with complex amplitudes. And rule number two says that rule number one only works when you're not looking. So this gave rise to the famous quantum measurement debate that lasted over close to 100 years and sort of was settled in the 70s by 70s and 80s by Bell Measurements, which was given the Nobel Prize a couple years ago. So it was Niels Bohr who famously said, we're all agreed that your theory is crazy. And this quantum measurement, in my opinion, still has many open questions, which we'll touch upon a little bit at the end, which is in the many-body setting. How does partial projective measurements entangle and disentangle the many-body system is still very interesting. So there are many hardware platforms trying to build quantum computers, quantum sensors. They range from solid-state systems to cold atoms and ions and photons and MV centers. So some of them are better for precision measurements, and some of them are better for quantum computing. Some of them are good for both. We've seen very rapid progress in recent years. This is a graph just showing a few leading groups in the US on neutral atoms, superconducting qubits, and ion trap qubits. And we are so a lot of people claim that we're in the era of quantum advantage, but I put a question mark because there are still many problems and challenges. So quantum advantage was a topic given to this random circuit sampling and other sampling tasks that was specially chosen to basically make it hard for classical computers to sample. And a quantum computer can, in principle, be exponentially fast, but the problem is lies really within the errors. So right now, for example, in Google's earliest result in 2019, the random circuit sampling had an error rate or had a success rate of less than a part per thousand. So, that is a little bit like maybe some of you have heard of the novel Hitchhiker's Guide to the Galaxy, which had a supercomputer that can compute the ultimate answer to the universe, and it computed for many years and spit out an answer 42. And nobody understood what it meant. So we're not guaranteed to have the right result in current quantum samplers, which is really the problem. So they come from both errors and verification, that we cannot verify a current state-of-the-art quantum computer's result easily. So one way of dealing with these errors would be to make the qubits logical, which is to stack up physical qubits and then use quantum error correction codes to turn those into logical qubits, which, given that we have sufficient physical qubit fidelity, the logical qubit fidelity will improve at a cost of course, there might be a certain encoding rate. For example, Google's recent work had about 100 superconducting qubits, and it reached this phenomenal result of beyond break-even, meaning that the logical qubit will get better than the physical qubit as the system scales. And there are some other codes, other systems which has better encoding rates. For example, they used in this work with trapped ions by Quantinuum, they used 52 physical qubits to encode 50 logical qubits. This is not published yet. And in the work in neutral atoms, the latest works used 448 atoms. And in fact, this 48 logical qubits was encoded with plus atoms. So the coding rate is a little bit better, but there is an overhead cost. So some of you might have seen this slide from yesterday, that we have a few gaps to really reach a fault-tolerant quantum computer that can run Shor algorithm to tackle with the factoring problem. And there are many groups in different places in the world that are all working on this. So next, I want to talk to you about this importance of dimensionality and qubit connectivity. So, as many of you know, dimensionality and quantum criticality have profound impacts. Dimensionality has profound impacts on quantum criticality. Well, even classically, the Ising model has no phase transition, and 2D shows phase transition. The Ising model has no phase transition in 1D. So quantum mechanically, of course, the Mermin-Wagner theorem states that continuous symmetries cannot be broken in low-dimensional systems with short-range interactions. So if you look at these suffixes, then we need either high-dimensional systems or better connectivities. So I sort of alluded to you this connectivity problem, and let's just expand a little bit, which is the fact that if we have a 2D nearest neighbor connected system, then in quantum error correction codes, the well-celebrated surface code doesn't have very high encoding rates. Whereas the work from the Harvard MIT group I mentioned to you before, when they're using high-dimensional code, for example, in this case, up to a 7-dimensional hypercube, then the encoding rate can be much higher. How is this done? Before I tell you that, I want to just show one example that the connectivity can be, in fact, a key to scalability. This was work done by my previous colleague at the University of Maryland, where they compared a superconducting qubit quantum processor with a trapped ion quantum processor with approximately equal fidelities, meaning that the gates and the measurements can be done with approximately the same precision. But just because of the nearest neighbor connectivity compared to the full connectivity, then at a given circuit with a trapped ion device, you can run with the better circuit fidelities. You can decompose the quantum circuit more efficiently. So at the state-of-the-art quantum processors, as you might know, are struggling for these fidelities. So it might be a key to shorten the circuit to reduce the number of gates, and this is also why connectivity plays a role. Now, in atomic qubits, in trapped ions, how are they connected? Well, in fact, because these are charged atoms, they have Coulomb interactions, which are naturally long range. But the problem is that much like when I'm talking with the microphone in this room, with the speaker in this room, all of you can hear me, but it becomes much harder to isolate two and only two people for the information to propagate. So essentially, the ions have to be shuttled. They have to be moved around by this complex geometry. Sorry, not complex in the mathematical sense, but complicated, I should say. Complicated electromagnetic trap so that pairs of two ions can be segmented and can be isolated. And by moving the ions, they can still be fully connected, but then the overhead cost is, well, you have to make this complicated trap for controlling 50 ions. There was significant engineering effort to have a trap of 300 electrodes. So they have some 200 people in the company making this all work. And then with 90% of the time spent moving the atoms, moving the ions, you can make a circuit. So with neutral atoms, it's essentially a similar idea. Previously, I just showed you this so-called quantum charge coupled device, QCCD architecture. And it's actually, with the neutral atoms, this was led by the Harvard and MIT group that basically has several zones. You have the storage zone, you have the entangling zone, you have the readout and reservoir, different zones, so that atoms can be moved around, for example, from the storage zone to the entangling zone, so that you can make a so-called transversal gate to run the quantum error correction operations. Oh, this computer is running out of battery. Thought it's connected. 这个是，那是不是没摁上？ Oh, okay, there we go. Sorry about that. And by moving the atoms around, you can put in this case, error correction codes in higher dimensions. Shown as an example, you can have the 2D color code and 3D color code. So, given that sort of background, I would like to share with you some of our previous work encoding trapped ion, encoding quantum information in trapped ion systems in high-dimensional spaces. So, of course, this is not a real physical dimension, but the ways that the qubits are connected. So, I'll show you how to do that. So, in terms of trapped ions, this is really a high-precision quantum engineering platform. In the context of quantum computing, they have the highest 2-qubit gate fidelities, above 3 nines. In fact, this is the highest laser gate fidelity. With microwaves, you can get even higher. With optical clocks, one can get the lowest systematic uncertainty, meaning that they're the most accurate optical clocks. They suffer a little bit from the signal-to-noise ratio because you have one and only one ion in this case for interrogating the clocks, but they're the most precise and accurate. Well, maybe accurate is the word. It is also a platform that satisfies the De Vincenzo criteria, 5 criteria for quantum computation and 2 criteria for quantum communication. It satisfies all of these. So how does this system work? Just very brief atomic physics, so bear with me. So the all the atoms are identical and precise, and that is because we use these, for example, ground state energies. Why they can make very good clocks is because this frequency is universal. It's the same in the US, it's the same in China, and it has a very precise number that can be measured to many digits. So in the case of ytterbium-171, which is one species of atomic ion that I used in my previous works, we trap this under an electromagnetic trap. So this is, you can see this is a ceramic structure with the gold plating providing the electric fields. There's a combination of oscillating and static electric fields, and the ions form this kind of self-assembled structure. It's called a Coulomb crystal. So they repel each other, and we squeeze the trap very hard on the radial direction to make them linear. All right, so we can measure these atomic qubits with very high precision with a relatively simple method, which is to shine state-dependent fluorescent light. So the light only couples to the upstate in the qubit manifold. And so if the ion is bright, we call it 1. If it's dark, we call it 0. So this can be done also with above 99% fidelity. How do we make the ions interact? So because these are charged particles, they share what we call a quantum bus, which is essentially the normal modes of motion. Now, these normal modes are classical, but we cool them down to the quantum mechanical ground state, and so that you can write these operators. You can imagine that when we shine two lasers on the ion chain, the spins start to couple to the motion, and this motion is shared between the different ions. So when we trace out the emotional degree of freedom, the spin states become entangled. So with that, we did some quantum simulations in the so-called dispersive coupling regime, which means nothing more than our laser detuning is a little bit far from the normal modes in the frequency domain, so that we excite the modes just a little bit and then trace them out. So summing over all the modes, you get this long-range interaction, which we used to study basically non-equilibrium effects such as this so-called discrete time crystals. So so back to the question: how do we isolate two and two ions only in order to form a quantum circuit? Well, there are pioneering works from University of Innsbruck and also from my postdoc advisor now at Duke University, Chris Moreau. Which were two different ways. So you can think about this as a graph that you can start with a fully connected graph and hide certain atoms, and that will be certain vertices from the graph. And then form a certain connectivity. Or the other way would be excite two atoms with the laser fields. But the problem is that all the normal modes of motion, because of the Coulomb interaction, is such a long-range interaction. All the ions will couple through the normal mode of motion, and you have to trace that out with certain numerical optimization techniques. So Ki-Won Kim from Tsinghua University and Roy Azeri from Israel, from Tel Aviv, came up with some different methods, and we also were inspired by this method, and also works done by the superconducting community, which is this connectivity. In fact, you can use that to program qubits into in this case. What was it? The negative curvature space. So so we were inspired by these works, and we said, okay, what if we play with the frequency degree of freedom, and so you can see that this is the horizontal line is as a function of the normal mode of frequency. So the so this was a motion picture, but because it's a PDF version, I will just show it maybe with my hand, which is the fact that you have a high frequency mode, which is a center mass mode. You can imagine that these ions are moving together like this. Okay, and the next mode will be a tilt mode, and the tilt mode, you can imagine that the transverse mode moves like this. The center ions stays fixed, so that you can in fact get a interaction that increases with the distance. So it is similar with the axial modes, except that with the axial modes, it's more separated in the frequency domain, so it's a little bit easier to control. So we made some numerical tests and showed that, well, if you want, for example, 6 qubits, and if you want to encode them onto a sphere, all you have to do would be to remove the 2 interactions that go across, well, actually 3, that goes across the 2 opposite ends of the sphere. So we can in fact realize that by coupling to certain normal modes of motion, this is the simplest example with 4 qubits, and we can arrange the center mass mode and the third mode, which has equal amplitudes and opposite signs, so that some of the interactions cancel each other. So when we remove these 2 lines, this will be 4 qubits on a square lattice, on the smallest plaquette of a square lattice. So we started by driving these modes respectively, and checked that indeed they evolve according to our numerical simulations, and then we look at the interactions of the ions. So this is a time evolution spins. We can generalize that by effectively having 6 and 8 qubits on a sphere and a hypersphere, and this is again the time evolving dynamics. So we can in fact use a flow K method to interleave XX and YY interactions, and we can use this method also to realize Heisenberg interactions. So this is a programmable, if you may, this is a hybrid digital analog quantum processor in this sense. So those were experimental data, and we wanted to generalize this to more interesting cases. And so in this case, we numerically studied what if we were to generate the interaction patterns in a tree graph. And in fact, also there can be different geometries, such as a triangular lattice on a torus. So you can see that there is some discrepancies, even numerically, and this is because that the frequency degree freedom in the end is not the full control degree freedom one would need to decouple the Coulomb interaction. So one would still need to move the ions around in order to realize higher scalable graphs. So this is pretty fun, but I would think that it is not only just for the fun of it, but it has potential applications in, for example, perhaps we can build a graph problem specific quantum optimizer. Perhaps we can start with a connectivity graph that is native to the hardware, and then we can massage that, we can tune that into some other interesting graphs by either hiding or numerical optimization techniques. So this is kind of a generalization of the previous idea. So now, do we have questions? If not, I will switch to the next part, which is 3D trapping of neutral atoms. So neutral atom trapping really emerges from this idea that we use light for quantum control. And so we all heard Steve Chu's lecture. And I was also lucky enough to have Bill Phillips in my thesis committee when I was at the University of Maryland. And those tools that they developed in the 90s have now advanced by a lot. In that there are new tools, for example, optical lattices can enable holding of individual atoms, and one can individually resolve the atoms when they are in, for example, optical tweezers. And we can have this so-called magic wavelength, which is widely used now in optical atomic clocks, and also the atomic detection method that I will be briefly mentioning towards the end of the talk. So in terms of quantum computing, it is a field with rapid progress, as exemplified by several research groups around the world and also in China. So atom computing and also Max Planck and also the French group in Paris, they have assembled of the order of 1,000 atoms with optical lattices, either in room temperature or cryogenic systems. Manuel Andres' group at Caltech in the US, they have trapped 6,100 atoms. This is phenomenal in terms of scale, and there's still more work in order to remove the entropies, because these atoms are filled randomly into the optical tweezers. And a Chinese group in USTC used AI-enhanced algorithm for 2,000 atoms rearrangement in parallel. So with these kind of systems, people have studied for example, quantum spin liquids, and this was enabled by already 2D moving of atoms. So you fill the atoms randomly, but you can have a target pattern of, for example, a triangular lattice or a Kagome lattice, and you can move the atoms into this shape and start turning on the interaction after that. And for quantum computing, as I mentioned to you before, one would need to rearrange the atoms after a couple of gates or even one gate in order to change the circuit. And then in addition, one would also have to move the atoms, say, between the storage zone to the entangling zone and to the readout zone in order to satisfy different functions in the quantum circuit. So we can also gain scalability. In fact, in my opinion, much better scalability in 3D. And this is just a particular example of using a device, so-called micro lens array. So you don't have to care about the details of the device, but there is an effect. There's an interference effect called the Talbot effect, which is the fact that by the time you've generated an array, one array of focused light, they in fact propagate afterwards and self-repeat. So this automatically yields a interference pattern of 3D optically focused arrays that you can use to trap atoms. And this was already demonstrated by the Darmstadt group in Germany, that you have many planes that atoms would stay in. And in fact, a different work done by the French group has shown a 3D arrangement. They've used a single tweezer to arrange the atoms into three-dimensional structures, including the Eiffel Tower, not shown here. So what if we combine these two methods, which is this micro lens array with 3D, and if we combine that with 3D atom moving, this will enable massively parallel rearrangement into entropy-free atom arrays, which is a key to scalability. So with this, we imagine that we would be able to arrange 10,000 or maybe even 100,000 atoms in a single shot, maybe in a few tenths of milliseconds. So we are building this kind of setup. So this is a cartoon showing the self-interference patterns of the array. And this is our vacuum apparatus, which we have already trapped atom arrays in here at BIMSA in building A7. And we're planning to use this so-called magic wavelength optical tweezer trap for state-sensitive optical potentials, which basically means that for atoms in the ground state and in the excited state, they will experience the same optical potentials. So what is this good for? This is good for the atom detection, which can be lost if you don't do it carefully. And with this magic wavelength, detection can be made a lot easier. So one has to care about quite a few experimental details when it comes to the realities in terms of 2-qubit gates detection and atom shuttling. Okay, so with this, I will provide a brief outlook, which is we are in this exciting era, and we're in this truly interdisciplinary field with many open questions. So we have the intersection of mathematics, information science, and many-body physics. So we want to find interesting applications of the so-called near-term noisy quantum era machines. And in the long run, of course, we want an error-corrected quantum computer, but there's many open questions as regards to what are the most efficient quantum correction codes, and how can they be efficiently, they can never be easily integrated, but how can they be efficiently integrated into our hardware? And then I want to mention this measurement-induced backaction, as I alluded a little bit early on, in the context of many-body physics. It's very interesting because one can, in fact, if one look at the quantum trajectories that the many-body system has gone through, then there can be entangling and disentangling. There can be phase transitions, many interesting phenomena. So I would then conclude here and just say that. I would say that the quantum many-body physics is still waiting for us to be studied. So with that, thank you for your attention.
Any questions? May I ask a question? So what are the biggest experimental challenges to maintain the quantum coherence and quantum control of the atomic system?
So the quantum coherence, among the two platforms that I told you about, these are all very coherent systems. The trapped ion system, people have demonstrated 1 hour of coherence. So the challenge really comes from isolating from the environment. So the atoms themselves are perfect, basically. But then we could have a little bit of magnetic field noise. In terms of neutral atoms, the problem, in fact, come from when you trap them with these laser fields. They can have fluctuations in the Stark shifts that they're generating. So if you have intensity fluctuations, for example, you will generate fluctuating effective fields, for example. So for atoms in this work I mentioned to you before by Caltech group, they demonstrated 12.6 seconds, which is limited by the lifetime. So that is another source of perturbation from the environment, which is the fact that we put the atoms in this ultra-high vacuum system, but so think about this. When you take a plastic bag, right, and you bag, say you have bag of air. That has a 10 to the 23 Avogadro's number of atoms in that bag. So we have 15 orders of magnitude better vacuum than room air. But then you still have many thousands of atoms colliding with the atoms for example, at any given time. So basically, you would they would escape the trap. Say if you have 10 to minus 11 tour of vacuum, you will have one collision approximately every 1 or 2 minutes. So this kind of external perturbation is still basically technical limitation to the system. That's why we want to do things fast, and people are also working on replacing the atoms and so on and so forth.
Yeah, thank you.
Yeah.
Any other questions? If there are no further questions, then let's thank the speaker again and thank all the speakers in the afternoon session. Thank you all.